to today's session where we will talk about the system classification and definition of energy storage systems. The content I am presenting today also can be found in the book Energiespeicher, Bedarf, Technologien und Integration that I have been writing together with my colleague Michael Sterner from OTH Regensburg and many other authors. Unfortunately, at the moment it's only available in German, but we already have translated all the content into English, and hopefully the English version of the book will be published in the next few months. Coming to the definition, a storage unit is a facility or a container to stock, store and preserve goods. When we relate that to energy storage, then energy storage is an energy technology facility for storing energy in the form of internal, potential or kinetic energy. An energy storage system performs three processes. First, charging or loading, then storing or holding, and third, discharging or unloading. These processes are physically implemented by energy converters, charging and discharging, storage units for holding, and peripherals. A complete facility including all three components is called an energy storage system. Charge, store, discharge. Energy storage system can all three parts be in one system, like that is a battery or a capacitor. They are charging, holding, discharging is the same. But it also can be different components. When we look, for example, the pumped hydro storage, then we have the motor and the pump that is charging the storage. We have the water reservoir somewhere in a higher location, that is the storage part. And then we have the turbine and the generator, that is the discharging part. But at least they are all in one place. Then we can think of other storages like the power to gas technology, where again we have three different parts, and then even the parts can be in different locations. So we have the charging, is the electrolyzer and maybe the methanization process. Then we have the gas storage that can be in a different place. And also the discharging, the gas turbine and the generator can be in a third different place. What else can we distinguish? We have a definition of primary storages and secondary storage. A primary energy storage are energy storages which can be only charged and discharged once. That is the typical consumer batteries, for example. What we require for the energy transition process are secondary energy storages. That are energy storages which can be charged and discharged multiple times. Then we have the so-called sectoral energy storage systems. And these are energy storage systems used only in one energy sector. With these storage systems, both charging and discharging occur in the same sector. So we have a storage system only in the power sector. That can be pumped hydro storages, that can be a battery storage, or it can be a supercapacitor. It keeps everything in the electricity storage sector. Then we have the heat sector, where we produce heat, store heat, for example, in a hot water tank, and also use it in the heating sector as heat. The same, we import gas from other countries, store the gas in our country in salt caverns, and discharge the gas in gas pipelines again. We have the gas sector. Or the transport sector, where we have oil tanks, fuel tanks, and everything is kept in the in the transportation sector. Then we have cross-sectoral energy storage systems. These are energy storage systems that may be used in more than one energy sector and in one or both directions, thereby linking two or more sectors. charging and discharging do not necessarily occur in the same sector. And sector linking connects the electricity, heating and transportation sectors with the non-energetic consumption of fossil raw materials, especially for example in the chemical industry, using energy storage systems and energy converters. Renewable electricity is typically used as a primary energy source to decarbonize other energy sectors. And this is an overview of coupling of different energy sectors. When we start in the upper left corner, we have the power sector. Of course, we might have again power storages like batteries, but then we can also connect the heating sector to the right upper corner, either directly converting electricity to heat and apply the heat, or produce heat and store the heat to use it later in the heating sector. Or we can combine the power sector with the gas sector by a power-to-gas process, either for hydrogen or even methanization, to store then the gas and maybe to reconvert it later to power in a gas turbine. Or when we have produced the gas, it also can be used for heating houses in the heat sector, or in the transportation sector to drive gas-driven cars, for example. And then also starting in the power sector, we might have a linkage to the transportation sector when we have electromobility by batteries that are implemented in cars. Or we produce liquid fuels out of power to liquid, and fuel then our liquid fuel driven cars. So there we have interlinkage of different sectors, and that might reach to an overall energy system that is much more efficient. In all sectors we have long conversion change from the very primary source, that could be for example the sun, solar energy, until the usable energy that is on the complete other side of the chain. And along the conversion chain from the primary source to primary energy, to secondary energy, to final energy, and finally the energy usage, in each step, or in most cases in each step, we can have a storage implemented. And in an optimized energy supply system, type, place and sector for the energy storage systems need to be carefully selected. Coming to the classification of all the storages we have, we could start with mechanical storage systems. So either we can store energy by different positions, it's the potential energy, or by the speed, then it's the kinetic energy, or by a thermodynamic state, for example, when we have the pressure of a media that is stored. For the thermal storage systems, we have either sensible heat, and sensible heat storage systems store energy with a medium changing in temperature before and after charging, which can be sensed. This is multiplied by the heat capacity and the mass of the medium to determine the amount of energy stored. Sensible heat storage systems such as hot water tanks are found in almost every home and require adequate thermal insulation. On the other hand, we have latent heat storage. Latent heat storage systems store energy without the medium changing in temperature, which cannot be sensed. Charging and discharging involves changing the state of the medium, as in phase change materials, short PCM, and using the resulting enthalpy. In buildings, latent heat storage systems can store and release heat with small temperature differences and have low self-discharge rates. And then we have, not that common so far, the thermochemical heat storage systems. Thermochemical heat storage systems use thermoreversible chemical reactions. So the storage system is charged by an endothermic reaction, absorbing the resulting enthalpy, and this is then discharged by an exothermic reaction. Another way is the direct electrical storage systems. That is either capacitors or superconducting coils. And these are the only systems that directly store electrical energy in electric and magnetic fields. All other storage systems require additional conversion processes. Then we have the very popular electrochemical storage systems, and also here we can distinguish different types or subdivide them in low temperature batteries, like we know from lead acid, lithium batteries or nickel batteries, or high temperature batteries like the sodium sulfur batteries, or we can also distinguish redox flow batteries like the vanadium flow battery. In electrochemical energy storage systems such as batteries or accumulators, the energy is stored in chemical form in the electrode materials, or in case of redox flow batteries, in the charge carriers. Then we have the chemical storages, and there we can distinguish according to their physical state. We have the gaseous chemical stores like natural gas or hydrogen. We have liquid chemical stores like methyl alcohol or kerosene, or we have solid chemical storages, for example biomass and coal. Chemical storage systems contain primary or secondary energy converted into energy carriers with high energy densities. So again, to sum up, we can distinguish energy storages by the physical form. There we have the mechanical stores, the thermal stores, electrical stores, electrochemical stores, and the chemical stores. What else can we distinguish? For example, according to energy and power. And to make that a bit more clear, we just compare that with liquids. So energy could be compared with the capacity or the volume of a container. And the power is more the diameter of the drain where we release the water or the liquid. So what we see in the picture, on the left side we have a schnapps glass, and there the volume is small, so low energy content, but the power is medium because the opening is quite high, so you can empty it very fast. Then we have in the center a bucket, and it has a medium capacity but a very high power because it has a very big opening, and so you immediately can discharge this. And on the right side we have a barrel, and that is the one with the highest capacity, the highest the energy content, but the drain is very small, so the power that we could release from a storage like that is very small. And the same comparison, but not with water, we can find with all the energy storages we just have distinguished from a physical state. Then we compare them on a temporal state. And there we talk about short-term storages, medium-term storages and long-term storages. Even there is not really a definition where is the barrier between short and medium between long. Typically only in the range of milliseconds to seconds it is what we have capacitors, superconducting coils. Then more on the medium side we have the battery systems, we have the pumped hydro systems, and then going from medium to long term we come to thermal stores, where we have sometimes only for a few hours, but we have thermal stores reaching up to seasonal storage, and then gas storages which have a very high energy density where we can store again over seasons or maybe even years. We also have the spatial classification, so we could have, for example, stationary energy systems, that is the most cases, or sometimes we require mobile energy stores, like here in the picture. So we have mobile and stationary systems, or we can also distinguish centrally installed or decentrally installed systems. One big central or many smaller decentral stores. And finally, we have the economic classification, and that is quite a complex matter. And at the end of our course, somewhere in January, we will have a complete section only on economic classification, economic calculation. And there we find then also the answer why we have so many different energy storage systems, all have their specific application. Storage economics is a quite complex matter, and quite often, and that is completely leading to wrong conclusions, only the investment costs, for example in euro for a kilowatt hour of storage capacity, are taken into account. But to judge on the storage economy, we need to take also into consideration not only the energy related costs, but also the power related costs play a big role. So the charge and discharge components of a storage. The lifetime of storage systems differs quite a lot. The efficiencies of charging, storing and discharging components is different. They have very different self-discharge rates, which is extremely important when we talk about the time between charging and discharging. The number of cycles, of lifetime cycles, storage technology can withstand. And then also the energy market boundary conditions, the prices for energy that we charge and get back when we discharge, plays a role on which energy system we will choose for a specific application. And so the next video will deepen the classification matters by comparing different energy storing systems. Thank you very much for your attention.